Hello everyone, welcome to this tutorial. In this tutorial, we will continue from where we stopped in the last class, right? In the last class, I introduced water electrolysis modeling, right? So we will continue from there. So before we continue with the modeling, I would like to give a brief description of the whole process, right? So now, water electrolysis is a technique that is used for the production of hydrogen, right? Green hydrogen, right? So it involves the dissociation of water into the respective ions, that is the H plus and OH minus ions, right? So through that process, hydrogen is produced, right? And it is seen as one of the sustainable ways to actually produce hydrogen, or it has that potential, right? And then for water electrolysis, we have a couple of methods that are being used, or techniques that are being used in the dissociation of water. So we have the AEL, we have the PEM, the AEM, and then the solid oxide electrolysis. So AEL stands for the alkaline electrolysis, which is like the most commercialized electrolysis method that is in use at the moment. It involves the use of an alkaline medium and typically occurs at temperature ranges of 65 to 100 degrees Celsius and then 25 to 30 bar for pressure, right? Then you have the proton exchange membrane electrolysis, of which requires a solid electrolyte, right? And it typically occurs at 70 to 90 degrees Celsius and then 30 to 80 bar, right? Then you have the anion exchange membrane electrolysis, right, which requires a solid polymer electrolyte, right? And then it also occurs within the range of 50 to 70 degrees Celsius and then 30 bar for pressure, right? Then also you have the high temperature, high pressure method, which is the solid oxide electrolysis, which usually requires a solid electrolyte, right? Typically occurs at 60 to 1000 degrees Celsius and then 1 to 30 bar, right? So these are like the major electrolysis methods that are already in existence, and it's important to note that I think most of them are actually still under they are still in their research and development stages. Apart from the alkaline electrolysis, which is already commercialized, these other ones are still in their research and development stages. People are still doing research to find ways of making them better, right? So that's that for the water electrolysis methods. Then now for water electrolysis, the major equipment that is used in the process is called an electrolyzer, right? So the electrolysis of water takes place in an electrolyzer. Now you are expected to model an electrolyzer in your process modeling software, but most likely you may not really have an electrolyzer in your software, so you would have to make do with other equipment that are actually embedded in the software, and that is one of the things that I will be showing you in this particular tutorial. Now, before you start your modeling for electrolysis, electrolysis of water to be specific, there are some parameters you have to determine before you actually start. Yes, very important parameters like the cell voltage, the power requirement of the electrolyzer, then the conversion of water into hydrogen gas. Now, the cell voltage would help you determine the power, right? So if you are able to determine your cell voltage, you would also be able to determine your power. Then also with your power, you can determine the conversion of water into hydrogen gas, right? So for this, you may want to use certain formulas that are embedded in research papers as regards water electrolysis. So I may want to recommend a few for you, and then you can also comment in the you can request in the comment section if you want to get the links to those papers. So I will just be showing them to you now, right? So this is the first, I think. Yes, so you can take a look at it. You can maybe pause the video to look at it properly. So this one is renewable hydrogen production processes for the off-gas valorization in integrated steelworks through hydrogen intensified methane and methanol synthesis. So it has a couple of yes, electrolysis models in it, right? Let me reduce this a little, yes, so you can see it properly. So yes, it has a couple of them here, so you can actually check for this particular paper. Paper is by Antonella. Yes, Antonella. So you can check for it using the name. Then we have this one too. Yes, this one has the formulas for those parameters. Yes, it does. So you can get some of those formulas from this particular journal. So the name of this one is Mathematical Modeling and Simulation Analysis of Advanced Alkaline Electrolyzer System for Hydrogen Production by Al Hassan Salami Tijani et al. So you can also check for this one. Then you can check for this one as well. This one too also has those parameters and their formulas. So you have the formulas embedded in this too. So you can check for this one as well, right? So this one is Aspen Plus model for an alkaline electrolysis system for hydrogen production by Monica Sanchez et al. Right? So you can also look out for this particular journal. So if you still maybe you need links to these journals, you can also comment in the comment section and I would respond to you, right? So back to the modeling of the process. So we are going to model a simple alkaline process in this particular tutorial. Now before we go further, we can look at what the electrolyzer looks like. Let's just take a look at it a bit. So this is what you have as your electrolyzer. A typical electrolyzer looks like this. So you have your electricity source, which is usually direct current. Then you have your feed into the electrolyzer. Then you also have catalysts too. Yes, so you have your feed. Now your feed enters and is dissociated into the positive and negative ions. Now you have water. For outlet of the electrolyzer, you have water coming out with hydrogen as well as water coming out with oxygen, right? So if you want to model this in the software, you will need a conversion reactor that actually converts the water into hydrogen and oxygen. Then you also need separators that would actually separate the water from these produced gases. So these are the things we'll be modeling in this tutorial. So we can move ahead, right? Let me see. Okay, so we have this. So in the last tutorial video, we already added the components and also the required reaction sets. The reaction sets and the chemistry sets were already added, so you can find them here. This is your dissociation. This is your water dissociation. Then you have that of the alkaline medium. So we are still modeling alkaline electrolysis. So we can go quickly into the simulation environment so that we can just quickly start off. So we are typically working with okay, we can work with both we can work with water and KOH coming in from another stream, right? Okay, so we begin the model now. Yes. Okay, so we start with atmospheric conditions. Yes. Okay, so let me use, I'll just use let me use mass flow instead. So this is the water stream. Okay, yes, I want to change this, so we can now specify the composition of water. Yes, so we have this and we are good with this. Then we can specify for KOH too. So this is for KOH. Yes, so still atmospheric conditions. Yes. Okay. 1 atm. Then molar flow. Let me just use this for molar flow. Then composition. Okay, that's for mass flow. Yes, mass flow. Then composition, KOH is 1. Potassium hydroxide is 1 for the mass. Yeah, the fraction, the composition. So both of them will be sent through a mixer. Both of them will be sent through a mixer. Let me reduce this a little. So they are being fed through a mixer. So I'll just name this mix out. Then let me see. Okay, so you have your KOH and water coming through. So you can check the worksheet. Yes, so you see the composition. Let me see. Composition of, okay, so let me see the composition from here. Okay, so we have the mole fractions. I think I want to change it to mass fraction and see what it looks like. So you have water at 0.83 and KOH at about 0.167, right? I think there is a ratio of the amount of KOH that should be in this medium, should be about between I think 25 to 35%, right? The alkaline medium. Yes, so when you are modeling yours, you should find out the required amount of alkaline that should be sent into the process, right? So there is actually a specified range for that, right? But I think I can continue with the model. So we have created our mixture of both water and KOH. Now we can so we are going to be modeling alkaline electrolysis. So we're using the process conditions of that. So we can, I think we can pump. Yes, we can pump first, then we can heat later. Okay, so for this we can use let's see what we can use. So we can use, okay, let's use 27 bar for this model. Just use 27 bar. It's within the range. So we have outlet. Yes, it's within the range, so we can use 27 bar. Okay, so the energy stream is Q1. Yes, then we can specify outlet pressure as 27 bar. Okay, yes, so that is 2000, that's 2700 Pascal. So we have a slight issue here. We have vapor in inlet stream, so I want to try to correct that. Let's go back to the mixer. So for the mixer, we specified 25 degrees Celsius for both inlet feeds, and then we have 114 as our outlet temperature, which is not normal. So I think I would want to add some water to this KOH stream. I want to add some water to see if it corrects that temperature. So I would reduce the fraction of potassium hydroxide here, KOH, and then I'll give some of it to water. So I have yes, I have 0.2, 0.8 potassium. Now I'll go back to check. Yes, I think it has even corrected now. So it actually reduced the temperature outlet to about 38.06, right? So I guess when you want to specify your alkaline medium, you can still add some water to this alkaline feed, right? In as much as water is actually the feed to the process, you can still add a little water to the KOH feed just to maintain the temperature of the outlet, right? And also remember what I said earlier, the weight percent of the KOH, there is a specific range for it. I think it's from 25% to 35%, right? So whatever you are having here for your KOH should be about 0.25 to 0.35, right, for this mixer outlet. So you would actually get that from literature, right? The required amount of alkaline that is supposed to be used in the process, right? So but this video is just for illustration purposes, right? So I wouldn't really dwell much on that. So we have solved that issue of the vapor in inlet stream, right, of the pump. So the pump are solved. So we have our feed at now it's at 27 bar. So we can now heat to desired temperature. Desired temperature is 65 to 100. Let's use 65. Let's just use 65 degrees Celsius. So we have H feed, yes. So we have H feed, then we have this. So unknown delta P, delta P can be 30 kPa, pressure drop 30 kPa, then worksheet we are heating to 65 degrees Celsius. Now this is it. So we have our process, right? So this is for taking the feed to process conditions, right? Taking the feed to process conditions. You pump, then you heat, then you can now send it into the electrolyzer or stack, right? So the stack is represented using a conversion reactor, right? Because you can actually determine the conversion using your power calculations, right? So I told you you have to calculate your cell voltage, then you use your cell voltage to calculate your power requirements. Then your power requirement is used to get the conversion of water to hydrogen, right? So that's how it works. That's the sequence. Then you need all of that in your model. You need to input all of that in your model. So that's how it works. So yes, you need an energy stream here, because this is where you specify your power, right? So I'll just use it as P. So P is our energy stream. Then our feed is H feed. Yes, then we can attach our reaction set. Is it set 1 or set 2? I think it's set 2. Yes, it's set 2. Water dissociates into hydrogen and oxygen. So it's set 2, yes. We specified Yes, let's view the reaction. We specified a conversion of 60. Now, this conversion here is an assumption, right? So conversion is one of the things you are supposed to determine before you start your model, right? So like I said, you determine your cell voltage. Cell voltage is used to determine power. Power is used to determine conversion, right? So the conversion you get from your calculation is what you would input in your equation, your reaction equation, right? When you are specifying the reaction. So you input your conversion there, right? So this is just an illustration, right? So then your duty now is the power requirement that you have determined from your calculation. We now need to specify the power requirement. So for this, I just want to make an assumption. You can either specify it from here or you specify it from the reactor itself. So either one works. Let me see. So you can specify it here. So I just make an assumption in kilowatt. So I just enter a value in kilowatt. So it calculates the liquid and vapor properties, right? So we can check the composition. So composition, you have your vapor of hydrogen and oxygen, mixture of hydrogen and oxygen, and then a little water. Then you now have your liquid outlet with water and the alkaline, right? So that's what we have here. Yes. So with this, we have modeled the electrolyzer. Now we need to separate the hydrogen from oxygen, right? So we can easily do that using a component splitter. Can just decide to use a component splitter to do that separation, right? Now, like I said at the beginning of the tutorial, you need to determine your power requirement, your cell voltage. Your cell voltage will help you determine your power. Then your power will help you determine the conversion, right? The conversion of the process, the conversion of water to hydrogen, right? So for this, I made an assumption of 5% conversion of water, right? So I changed it from 60 to 5, right? So like I said, you will be specifying power and not temperature, right? Because normally when you add an energy stream, you may want to specify the outlet temperature, but in this case you are specifying the power requirement of the electrolyzer, right? So, and you will determine that using your calculations. So the next thing is to separate the hydrogen from oxygen, right? So we can do that with a component splitter. Let me see. A component splitter. Okay, let's check here. Yes. Okay, so you have a component splitter. I will just use it to separate. So I'll name this H2, and then this I'll name it O2. I'll just name it O2, right? So I want my hydrogen to come out from the top. Then the inlet is the vapor outlet of the stack. Then I can just use this to create an energy stream. Then I need to specify the splits of the components. So I think hydrogen will be 1. Yes, from the hydrogen stream, hydrogen will be 1 and the rest will be 0, so that only hydrogen comes out from there, right? So you just do that. Then you can specify the pressure and temperature of the outlets. So let's say we have a pressure drop of like 30 kPa, so we'll be having 2640 here, right? 2640 as well, right? Then we can specify temperature. Okay, so let me just say the temperature is 70, so it doesn't really drop. Okay, so let me see. Okay, so it has solved, the whole model has solved now. So we have successfully separated the hydrogen from the oxygen and the other products. So we have the hydrogen coming out from the top, and then the bottom is mostly oxygen, right? So this is the stack or the electrolyzer unit, which consists of the conversion reactor and the separator. Now, when you do your calculations, perhaps you have a low conversion, you can decide to recycle your unreacted water back to the process, right? You can decide to add a recycle just to reuse the unreacted feed, right? And that's done mostly when you have a low conversion in your calculations, right? Maybe you do your calculations and you are getting a low conversion. You can do your recycling to still utilize the unreacted feed. So we can just quickly do that. Let me see. Okay, so this is this is a recycle. Okay, before I do the recycle, I want to do a little splitting of the feed. So this is it. Okay, I'll just turn this. Yes, then most of the water is in the liquid outlet, so I would, most of the water is there, so I'll just do this. Then I'll reduce the amount of water that is going back to the feed, right? So this is 3 and I want another stream 4. So I'm trying to split the amount of water that comes out of the conversion reactor, right? So I can specify the split or the flow ratios. Okay, so let me see, I use 0.5 for example. Let me just use 0.5. Yes, so half of what is coming out here is going to come out from these 2 streams. So here we have 57.14, right? So the top is 28.57 and the bottom is 28.57. So I will only send one of these into the feed stream because I suspect that sending all of it may be too much, right? So I would only send one part of it. So I just call this recycle 1, then I send only one of those streams, right? So I'm feeding only one of those streams. Yes, then I will now send this guy into this and see whether it solves. So I would yes, let me save it first before I do that. Control S. Yes, Control S. So in case it doesn't work, we can adjust the splits here. So I'll just click on this and then attach that stream, which is rec 1. I just attach it. Okay, so it's saying something here. Let's see what it's giving. Okay, vapor in inlet stream. To solve the problem, let me see if I can remove the oxygen that is present here. Some oxygen was present in this liquid stream, so I would remove it. Then I would now, maybe I'll cool it down before I now send it into this mixer, the feed mixer. So let me cut this off and leave it for later. So we get another component splitter, and then we so let's see, we can remove bottom. Okay, I'm trying to separate water from oxygen, so bottom can be, okay, bottom can be water, then the top can still be O2, but this time around I will spell it as oxygen. There is a little amount of oxygen in this water stream, so I will try to rectify that now. So this is QS. Okay, so that's that. Then we have unknown splits. Unknown split, for split, I want to separate oxygen, so it's oxygen will be 1 and the rest will be 0. All others will just be 0. Okay, then we can specify the outlet conditions. Okay, let me just say 2650 here and here too. Then the temperature, I don't need the temperature to change actually. I can just assume that the temperature doesn't change. So I just separated the water from the oxygen, the little oxygen that is in that bottom stream. So I can still try this again and see if it works directly. If it doesn't, then I have to add a cooler as well, right? Because the temperature of this guy is 70, so it may be part of what is affecting this. But let me just try it without using a cooler first and see what would happen. So this will be fed into the T, and then the feed will now be splitted into 2, because so that it's not too much for the process. That's why I'm trying to reduce it. I don't want it to be too much, so I want to start with a divided recycle. So we can now send this into the mixer. Let me check the split I used here. Okay, I use 0.2, so I can try with 0.2 first. Then if it solves, I can continue with other values. So let me see. Okay, so this one solved this time around. I think it was the oxygen feed that was the problem. I'm not sure, but I think that was the problem. So I think it solved this time around. Okay, now I think we can also increase it. We can increase the ratio now to maybe 0.5 that I initially assumed parameters. So I can increase it to 0.5, for example. Yes, and check if it's still solved. Okay, so it's still solved, it's still okay. So that's it. We can recycle some part of the water, the unreacted water, back into the feed, and then that would help to increase the production of hydrogen, right? So you have your hydrogen product right here. So you can decide to maybe pressurize it and then store it, or do whatever you want to do with it. So you have your hydrogen product and then your oxygen product, right? So this is just a basic model for the electrolysis of water using aspenisis in particular, right? You can also do something similar to this in Aspen Plus as well, right? So, but I specifically wanted to show how it is done in aspenisis, right? So, and in this electrolysis model, you have your electrolytes, like I showed you in the first tutorial. You have the electrolyte section because you used the electrolyte NRTL. So you have the electrolyte section in all of your streams, right? In all the streams, you have the electrolyte section. So this is what it looks like. You have the components, then you have the ions as well, right? So you have your ions, OH minus, H plus, H3O plus. You see it's 0 because it's not part of this process, so all the values are 0 for that particular one. Then you have your K plus, right? So all these all of these ions are here present. Then You have them for all your streams, right? For all the streams, right? You still have, if you check, you would find it in all of them. Then you have the properties of those ions as well, or electrolytes. So you also have them here in all the streams present. So if you check it for KOH, you also find it here too, right? So you see for KOH, the K plus has values, right? And then you have your OH values as well, right? So you have it for all of them. So typically this is how to model the electrolysis of water using Aspen-ICs. This is your product. This is the product specification based on the initial parameters I specified. This is the hydrogen produced, right? So you have your mass flow, your molar flow, and all. You can decide to reduce the temperature if you want, and probably increase the pressure to more than this value, and do whatever you like. You can decide to also increase the feed and do whatever you want to do with it, whatever analysis you want to do. So you can decide to also make the properties visible for your hydrogen product, right? So with this, we have come to the end of this particular tutorial. If you have a question on electrolysis or the modeling of electrolysis, you can drop your questions or observations in the comment section, right? Like this video, share with your friends, and also subscribe to this channel if you have not done so. Thank you for joining me in this particular tutorial. Do have a good day.